Hello. The purpose of this video is to serve as a bit of an introduction to the topological codes module and how it works. So it's in Qiskit, it's in Ignis, it's in the verification part of Ignis because it is intended not to actually correct errors, but as a way to see if your device is doing what it's supposed to be doing. And it's specifically the module called Topological Codes. And it's called Topological Codes because the intention here is to have only a quite restricted set of codes, although useful and popular ones, that all have the same sort of decoding procedure. Okay, so at the moment we've only got one kind of code, which is repetition codes. And of course you're going to hear my keyboard throughout this because I am live coding. So if we start up if we create a repetition code object, then we have to give two arguments. One is the number of repetitions, which is the number of code qubits in our code, and the other is the number of times we do the syndrome measurement round. So let's do 5 and 3 for completely arbitrary numbers. Now within this code object are circuits. So you have this dictionary of two circuits. One is the circuit which stores a logical 0, and the other is the circuit. So let's have a nice matplotlib output here. So this is a circuit which stores a 0, and this okay, so having 3 repetitions makes these circuits quite big, so let's make them a little bit smaller. And then this is the circuit which stores a logical 1. So let's start by having a look at these circuits. So what we see is that we have code qubits. So these are the qubits. They might also be called data qubits by some people. These are the qubits on which the information is actually stored. You also have what I've called link qubits. And these are the ancillas. So in a surface code, you might call these maybe plaquette and vertex qubits if you think of your stabilizers as plaquette stabilizers and vertex stabilizers. They're the ancilla that lives in the plaquette or the vertex. But in this case, we have a chain of qubits. So basically, to make a little ASCII drawing, we have a code qubit, and then sitting next to that, a link qubit, and then a code qubit, then a link qubit, then a code qubit, then a link qubit, then a code qubit. And so these 5 code qubits will either be all 0 or all 1, in that they're storing this repeated bit value. And then the link qubits are used to make parity measurements of neighbors. So this link qubit here will be used as part of a parity measurement where we're comparing the values of these 2 code qubits. And this link qubit will be used in a parity measurement for these 2 code qubits. And this link qubit will be used for these 2 code qubits, and so on and so forth. Okay, so we have our code qubits here. Of course, all qubits are initialized as 0, so these all go into the circuit as 0s. This is a circuit in which we are storing a logical 0, so we want to repeat this 0 value across the code qubits, so the initialization step is already done for us. Then we have to make the parity measurements. So the parity measurement means that code qubit 0 code qubit 0 and 1 will have a parity measurement facilitated by link qubit 0. So here we have code qubit 0, and here we have code qubit 1, and here we have link qubit 0. And what we expect to see is a controlled knot controlled on code qubit 0, targeted on link qubit 0, another one controlled on code qubit 1, targeted again on link qubit 0. So that computes the parity of these 2, and then you measure it, and then if you want to do this again, you reinitialize the link qubit and repeat the syndrome measurement, measure again, and so on and so forth. So that is what all of these measurements are doing here. Then when we do the final measurements of the code qubit, the link qubits, we don't have to do an initialization afterwards, and indeed we shouldn't, because the compiler will complain at us. And we're also going to just measure all of the code qubits, which is what we see here, and also I think one of them is here, to see what their values are. The logical 1 is exactly the same, except that we have to have a repeated 1 across our code qubits instead of a repeated 0. So the initial value of 0 that we get is not what we want, and we have to use an X to flip them all to a 1 instead. Oh, and another thing, when we make measurements, we have different registers to read out that information. So the code qubit information is read out into a classical register called code bit, and the first round of syndrome measurements are read out into a register called round 0 link bit, and the second round is read out into a register called round 1 link bit. So when we look at the results, we should know where they come from. Okay, so what have I imported so far? I just imported the Qiskit Ignis stuff. So let's import some other stuff from Qiskit. Import quantum circuit, which we need. Actually, we don't need quantum circuit at all. Oh well, I've typed it now. It doesn't do any harm. But we do need to execute, and we do need a backend, and I'll use the simulator air. So what we might want to do is run one of these codes. So let's do code.circuit 0 as the one we're going to run, and we execute that, and we execute it on a backend, air.get backend chasm simulator. A chasm simulator is a simulator which acts in the same sort of way as a real quantum computer, so it doesn't give us things like state vectors or density matrices. And then running the execute gives us a job. Let's do it explicitly for those who aren't so great at Qiskit. Running that gives us a job object, and then we want to have a result object from our job object, which means that we call this. But all we're interested in from the result object is the actual counts. So the counts is this histogram of what results we get, and that should do it. So let's now print counts. And what we see here is a result which is 4 zeros and then 4 zeros and then 5 zeros. And so what is happening is that we have these three classical registers: round 0 link bit, round 1 link bit, and code bit. And this is the results from round 0 link bit. This is the results from round 1 link bit, and this is the results from code bit. So these are our parity measurements in the first round of syndromes. These are our parity measurements for the second round of syndromes, and this is just the final readout of all of the code bits. And here we are running the thing for a logical 0. So all of our code qubits, will be 0 throughout. There are no errors. So the only reason why we get non-trivial parity measurements is because of errors. So given that there are no errors, all of our parity measurements come out as 0. So that's why we get this here. If we ran it for 1 instead, again, because there are no errors, all of our parity bits come out as 0, but all of our code bits are all 1s, reflecting the fact that we have got a logical 1. Now, another important thing to do is to process results. So we take our code object and we have actually what we should do is for log in 0, 1. So let's actually extract all of the results. We'll call this log. And then we're going to create a dictionary called raw results, where raw results for a given logical value is the counts value. So let's see what this does. Yeah, it's just the values we had before, but now together in the same object. And we're going to do this process results thing on raw results. And it gives us this. So this is a processed form of the results, which is in a way that the decoder is going to be able to make more sense of it. And the idea is that any codes that are put into this topological codes module should have a process results method which turns the results into a form that the decoder can easily make use of. So what is going on here? Well, here we have logical values and syndrome values. And so this here is the first round of syndrome measurements, the first round of results from these parity measurements. And therefore it is exactly the same as this. Of course, everything's 0 here, so it's going to be exactly the same. Okay, but these are actually exactly the same. These will always have the same value here and here. Now this set of values is related to this one, but it's not exactly the same. What we're looking at here is syndrome changes rather than syndrome values. So for example, if we had a case where we didn't get this result, but we got, say, this result. Now, okay, we got this, we got this. Why have we got that? It's going to look like something like that. So say we got this result out. What would this process to? Well, as I said, this set of values is explicitly this set of values. So we just copy this over. And what this is telling us is that, well, actually, this is a bad example. Let's have it that instead. Yeah. So, yeah, as I said, this set of values is this set of values. So we just copy it over. And what this is telling us is an error has happened, causing two of these parity measurements to give us values of 1 instead of 0. And then we rerun the parity measurements, and it tells us that those ones are still 1 instead of 0. So in this case, it's telling us something has happened. Something unexpected has happened. We expected them all to be 0, but 2 of them are 1. So an error just occurred. That's not what this is telling us, though. It's telling us everything's exactly the same as before. Okay, yes, an error occurred back in the mists of time, but we already told you that. Here, we are not presenting any new information. So what we want to do with this second bank of values is not just copy this, but we want to do this differences between this bank of values and that bank of values. So here it's a 1, yes, but we already knew that. So it's not telling us any new information. Here, this is a 1, but again, we already knew that. So it's not telling us any new information. And so for those cases, we put a 0. And these ones are 0, and they were 0. So again, no new information. But if these ones were 0 and the previous one was a 1, that would be a change. So then even though there is a 0 in the second bank of bits, we would still put a 1 in this processed form because we're looking at changes in syndrome value. So these are two banks of 4 numbers, or strings of 4 numbers, 4 bits, which represent parities. But you'll notice that in the processed form, there aren't just 2 of these. Actually, there aren't just 2 of these, there are 3. So what is this telling us? Well, here we can classically look at this and work out parities. We can do our own little detective work and say, okay, for these 2, because these are now code qubits, the outputs of code qubits we're looking at here, exactly the thing that we were looking at parity for when we do syndrome measurements. So for these ones, we can look at these and say, oh, there's a parity of 1. And then we can look at this pair and say, oh, there's a parity of 1. Then we can look at this pair and say, oh, it's parity of 0. And then finally this pair, and we see a parity of 0. And so we are doing a final measurement of the parity, not through C0 this time, but just classically through post-processing. And then again, we take this and we compare it to the previous one and we note down changes. And as we see here, there are no changes. So we just get this. And then finally, the next couple of values that we have in the processed results are a readout of the logical bit. Now there's only one logical bit, so you could only have one readout, but actually we're going to use two, and we just pick the endpoints here. So for this, we should have the same bit value repeated across all of the code qubits. And so looking at any of them in isolation should, in an ideal case, be enough to read out the logical value. But if errors happen, then that means that this is not necessarily to be trusted. So for example, if we use this one, we would conclude that this is a 1, where in fact it should be a 0. So we're going to use the ends to have this uncorrected readout. And then that is the form of the of the processed results. You have these two different opinions on what the logical readout should be. You have then a gap of 2 spaces to denote that now we're going into the syndrome measurements. And the syndrome measurements are the first set of syndrome measurements, and then the difference between the second set of syndrome measurements and the first, and then the difference between, and so on and so forth for the third and the fourth and whatever. But the final one is again a set of syndrome measurements, a set of parity measurements, but this time ones that are manually done, or at least classically done, from the final set of code qubits. Okay, so that is what the processing looks like. And the reason why it's done in this way, and the way it has to be done in order for and so you can see that the logical one differs only by the fact that its logical readouts are different. The reason why this is done is such that whatever results you get, if you inject just a single Pauli error at any point in the circuit, you'll always get a processed result which has 2 of these values changed, in this case these 2. And I actually have this whole thing, this whole block of code, which I basically stole out of, like if we go to the source code, if you go into fitters, this is the source code for the decoder. And what I'm about to show you is basically stolen out of here. So it's under the hood of the decoder. And what it essentially does is inserts, so I've done it in the form of a function, and this function given a code and a decoder. Actually, it doesn't use a decoder in this form, so let's just get rid of that. What this function does is it takes this code and it takes the circuit for a logical 0, and then it creates a blank circuit which has exactly the same registers as the original circuit, and then it goes through and injects an error. So it injects a single Pauli error, and it loops over all of the different places a single Pauli error could be inserted into the circuit, and inserts it. And then what we get at the end is it executes all of those circuits, and then it looks through all of those circuits and looks at the results and looks at the processed results, and then gives all of that to us. So let's use a slightly smaller code as we look at these. So let's, for example, let's just repeat all of this, but with a d equals 3, t equals 2 code, so 3 code qubits and 2 measurement rounds. So exactly the same, except we've now got less code qubits. And so now we've only got 2 parity measurements and 3 code qubit results. Let's get rid of them. And let's run it and see what happens. So now it's making the circuits, it's listing them all together, it's running that big giant list, and therefore it takes a little while. But these are Clifford circuits. All of the gates involve the Cliffords. There's the controlled not, so the X is measurements, and there is the Pauli errors that we're inserting. And so everything is Clifford, and the simulator fortunately knows when it's given a Clifford circuit to run it a bit more efficiently than it would do otherwise. However, it is, as you can see, still taking a little bit of a while. It is going, right? Okay, apparently, I only defined the function. I didn't actually run it. So that will account for the fact that we're not seeing any results. Let's give it a little while. And the really important reason for this sort of process, and the reason why it's actually in the source code for the decoder, is the decoder runs all of these circuits in order to work out exactly how errors affect the code. So, for example, here's some things we see. So if we have an X which is affecting code qubit 0, which is the one that gets read out over here, then what happens is that X gets its value flipped. It is a 1 instead of a 0. It also means that one of the parity measurements picks it up. Only one, because the qubit on the end is only involved, if we go up here, this code qubit is only involved in one parity measurement, the one whose ancilla is here, because it's on the end. So that single parity measurement will pick up on the fact that an error has happened. It'll pick up on it again when we do the process form using the results from the code qubits. It will pick up on it again, and also we see it in the final readout. Also, because it's one of the end qubits, that means that one of these two votes on what the logical value is also flipped. So when we look at the processed results, we find that it sees a single parity get flipped. There is no further change in the subsequent rounds. And then we see that one of our logical values is different from what it should be. So, as I said, two of these numbers are getting flipped. If we have a Y in the same place, the effect is the same. If we have a Z in the same place, there is no effect, and so on and so forth. We can get all kinds of stuff going on here. So here, for example, is a Y on qubit 2 inserted at depth 3 in the circuit. So this depth is just in terms of the list. It's not actually depth. I shouldn't really have used that word. It's actually, you take the circuit as a list and you say, okay, 3 into the list. We insert a Y. So this is then list 1. This is 2. This is 3. So it's possibly now after here. So in the midst of these. And what effect did that one have? I chose it because it had an effect, but not on the logical values. Yeah, so here we see that it gets seen by one of the parity measurements, but not in the next round and not thereafter. So effectively, we have one round of parity measurements saying, hey, something's wrong. And the next round of parity measurements here says, actually, no, nothing's wrong. So this was unexpected because we saw something happen. But then this was unexpected because we expected that error to still be there. And so we see that in the list of syndrome changes, it comes up twice. And then in the final one, it's still not there, but at least we expect it not to be there then. So again, we now have two things popping up. And this isn't so much that an error happened on a code qubit and caused a pair of parity measurements to flip, as we typically expect in these things. But this was more an error on one of the ancilla qubits, which effectively caused our parity measurement to lie to us, and so on and so forth. These are all of the different results, and it's with these that the decoder is defined, because now the decoder can set up a list of possible ways that errors can affect the code, and with that it can try and deduce, when given an actual noisy measurement, what has gone wrong. So it could just be that it gets given this and it says, oh, I know that. It's an error on qubit, and it's an X error on code qubit 3 at this particular point in the circuit. So it will be able to deduce, or equivalently you might think it's a Y, because both of those have the same effect here. Yeah, but it already knows that error, so it knows how to deal with it. But you might get a combination of things. Like you might get a combination of, let's pick a couple out, this error and the error that we just saw here. So this error. What happens if we get a combination of these two errors? We would get a so we're X on 3. So X on the code qubit register at 1 at depth 15 gave us this final result. And on code qubit 2 at depth 16 we got this final result. So these are the processed results I'm getting here. So what then if we gave the decoder this as a final result? 1 0 0 0 0 0 0 1. This is the combination of the two above. So we take mod 2 on each of these. So these two mod 2 is 1, these two mod 2 is 0, 0, 0, 0, 0, 0, and 1. So what if we get this? What will a decoder conclude? What will it think was the original, what was the error that caused this? Well, it will see, well, it knows that, well, let's give each of these ones a name. So let's call that one. We'll define them by a set of coordinates, and if they are over here, we'll use the coordinate 0, and if they're over here, we'll use the coordinate 1. So it's here in the parity measurement, so we give it the coordinate 1. And then we give it the coordinate according to what measurement round it's on. Measurement round 0, measurement round 1, measurement round 2. So that's a 2. And then we give it coordinates based on its location here. So this is location, I suppose I should do location 0 and location 1. Although I may have been inconsistent when I actually defined the thing and did it the other way around. But at least in this context here and now, let's do that. So the 2 points we see here are 1, 2, 0 and 1, 2, 1. And we know that these are connected. If we think of this in terms of a graph, we can think of a graph where 1, 2, 0 and 1, 2, 1 are names of nodes, and there is an edge between those two nodes. Now there's all of these things go into creating the entire graph, but this is at least one little part of the graph. And then here we also have another little part of the graph. Again, we've got 1, 2, did I call that 1, 2, 0 or 1, 2, 1? Okay, I'm going to call this one 1, 2, 0. And this one is something else. This is over in the logical, so it's got a 0 here. And it's the first of the logicals, so we'll call that 0. And it's, well, there's only one of them, so also 0. So that's called 0, 0, 0. That's another edge of our graph. So given that those two things are true of the same code, then this means that we can define a graph that has all of these edges. And of course it has a whole bunch more, but these are the only two that are relevant, so let's just focus on these. So we've got this one, and this one. And we need a way to resolve all of these points. We need a way to do a matching. And yeah, but the matched ones only need to be the ones that are actually involved in an error. And what we find in this case is that the only nodes we have are this one and this one. So the 000 node and the 121 node. And so from this, which is effectively our what we call a syndrome graph, we need to determine what we call an error graph. And the error graph involves only nodes that are present in the final readout that we get, the processed form of the final readout. So in this case, our error graph will only contain the nodes 000 and 121. Oh, sorry, 121. And it will contain an edge between all pairs of nodes, and the distance, so the weight that we associate with that edge, corresponds to how distant they are on the syndrome graph. So on the error graph, we can think of it as being completely connected, but it's a weighted graph. All of the edges have a weight, and the weight corresponds to how distant the 2 points are on the syndrome graph. So we can see that 000 and 121 are 2 edges away in this case. So that is what we put in the syndrome graph. And then we have to do a matching, which matches up all of the points in the error graph. Although it's not completely a minimum weight perfect matching, or it's not completely a perfect matching, because we don't need to include these ones. If it's possible to do a matching which involves all of the ones that are syndrome ones, so ones with a coordinate 0 here, without using any of the logical ones, then that is fine. But we do need to use up all of these ones. And basically what decoding is trying to tell us is whether we need to involve these ones or not. So in this case, there's only matching means actually just pairing these two up. So obviously, in order for this one to be involved in a matching, this one also needs to be involved. And what we determine there is that this logical value is not to be trusted. And it's telling us that the logical value is 0. We know it's not, it's telling us the logical value is 1. We know because it got involved in the matching, it's not to be trusted. So the logical value is actually, as the other one says, a 0. So now we have been able to deduce how to decode something which was not just a result of a single error. It's not just a result of something the decoder's already seen by going through all of these single errors, but it's decoding something that it's been able to see by having multiple, when there are multiple errors involved. And so this is basically what happens in this decoder. It creates the entire syndrome graph, not this tiny little subset that we are looking at here in this example, but the entire syndrome graph by taking the logical values, by looking at the output results given every possible single qubit error that we can insert. And then given an actual thing to be decoded, it creates an error graph that only has nodes corresponding to things that are actually in there. Actually, it always has nodes for the logicals. So that's actually one thing that I should have noted here. So there's also the other logical 0, 1, 0. And so there's, in the error graph, we have nodes for everything in the syndrome part, that is 1. And we always have nodes for both of the logicals, whatever their value is. Because they could be 0 or 1, we don't know what we've encoded. And the distance between the logical 0 and the logical 1 is the weight of it's basically the distance of the code, which in this case is 3. So there is that. And then there's also there will be another edge between these two of weight. well, whatever it is. But whatever it is, still the solution to the matching is to match up these two and deduce that this particular logical value, sorry, that should be 110. This particular, no. That is a syndrome. This is the one that is the one not to be trusted. So this is the name of this. So I made a little bit of an error there. Yeah, but still the matching that is the correct solution will be to match these two up. This is optional whether it gets involved or not, and so we take the option that it's not involved because whatever this weight is, and I'm having a bit of a mind block on how to create that weight at the moment. Whatever that weight is, it is too large to be able to overcome the fact that this is matched with weight 2. So yeah, we take the syndrome graph using all of the possible ways, not just these 3, but all of them. All of these results are used to create the syndrome graph. The error graph has everything in a node corresponding to everything in here that is 1, and then both of these. And then you have to do some minimization procedure which collects up all of these syndrome nodes into neutral clusters, so clusters that have an even number of, in this case, an even number of points, so a matching, for example. So you can do some form of minimum weight perfect matching. It's not a perfect matching because it doesn't have to involve the logical nodes, and then it's whether or not the logical nodes have to be involved, tell us whether or not they're to be trusted. So it's all a graph theoretic minimization procedure on a graph that we construct using the properties of the codes when single qubit errors are inserted. Yeah, that is some stuff on topological codes, and I hope it makes things a little bit more easy to understand. But as you see, even here, there are so many different places you can insert an error. The graph here is going to be quite big. And we can actually set up a graph decoder object. Here I've been talking about graph decoder objects without actually creating one. So let's create a graph decoder object for a code. And it takes a bit of a while to run because it has to do all of that stuff I just talked about. And then when it has done it, this decoder.s is a graph. So if we look at for v0, v1 in decoder.s.edges, and then we can print all of these, we can see the entire syndrome graph here. So it's not actually huge, but hopefully it does have these points that I said, 0, 0, 0 connected to 1, 2, 0, 0, 0, 0 connected to 1, 0, 0. Okay, so I labeled them wrongly. But yeah, I shouldn't have labeled them wrongly. So I should probably actually go into the source code at some point and relabel them to the way that I just described, because the way I just described is a better labeling. But nevertheless, all of these points are in there. These are edges in the syndrome graph, and then when we take something like this example that I just created here, we can use one of the methods. You can find all of the methods here. Oh, this is the methods of a network X graph. That's not what we want. So make error graph, for example, exists here. So we can do decoder.make error graph, and then we put in a string that we want to make an error graph of. and it has this, it comes out of a dictionary. This is also another imperfection in the source code that we should probably deal with. But until then, we deal with it. If we look at these edges, then we find out that I can't type. We find out that 0, 0, 0 is the only a logical that's involved here, and 0, 1, 0 is also involved, and there is some way to extract a weight, but I can't remember what it is. If we extracted the weight corresponding to this edge, we would also see that this is quite a high weight. This is weighted with the distance, whereas one of these, so this one has a certain weight which isn't so high, and this one has a certain weight which is a bit higher, meaning that the matching that we have to do on this particular error graph is to match these two, which means that we have got our single syndrome node involved in the matching, which is what we need, and it's matched up with this one. But yeah, I'm not going to be able to remember how to extract the weight, but I guess it's actually in here. It would be a good thing to be able to add this. So edge data, distance. Is this how things really work in the real world? Let's give it a go. So we actually, let's give a name to our error graph. Let's call it E. And then it's E that we want to get this information out of. So let's do that. And we see here that this one has a weight of 3. It's a distance of 3, so it's a weight of -3 because it actually does maximum weight matching rather than minimum weight matching. This one has a weight of 2, and this one has a weight of 1. And so the minimum weight perfect matching would actually match up these two. So it would actually tell us that this one is the one not to be trusted, which is the opposite of what I told you before, because I told you 0, 0, 0 is the one not to be trusted, but we have to remember I have labeled these things weirdly. The labeling I used here, which is the labeling that we should use, is different from the labeling that is actually used in the source code, which is something that we'll have to deal with. So that is unfortunate, but hopefully you get, nevertheless, the idea. And we could add different, we could add a thing in here. This would be equivalent to a single qubit error on the middle code qubit during initialization, which doesn't show up in the logicals and doesn't show up subsequently because it doesn't cause any changes. And this would give us a whole other set of edges, and we would have to work out how to incorporate that. But it would just basically mean the two nodes corresponding to these two ones should be paired up, and then otherwise paired up as it was before. So this is the way that the syndrome corresponds to nodes in graphs. There's actually 2 graphs involved, the syndrome graph and the error graph. It's on the error graph that we do the matching, blah, 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 blah. Yeah, I think I'll call it an end here.